we'll get started since it's pretty much on time. So just so you know, since there are obviously a plethora of talks to go see too, you're in the mapping and evolution of Android permissions. Andrew Reiter is, I'm Zach, by the way. Andrew Reiter is my colleague who also did a lot of the research that I'm going to present. We gave this talk at Black Hat Turbo Talks for like 15 minutes. There's a lot more content here than if you saw that version. So just to give you a little bit of background, Andrew and I are both security researchers with Veracode, where we do binary static analysis stuff, where we focus a lot on, we in particular focus a lot on mobile. And I'm a recovering consultant, so to speak, former net, web, app, mobile pen tester type. Andrew's all those things, old woo-woo guy, and we work there. So the agenda is we're going to talk a little bit about AOSP, which is Android Open Source Project. There's a reason that I'm going to intro that, just so it'll set the stage as to what this research actually focused on. We're going to talk a little bit about permissions in Android. This is not an Android talk in the sense of like explaining to you how the reference monitor works and stuff, but what problem we're actually trying to solve. The problems that surround permissions and some prior research from a lot of academics who use LaTeX a lot, and the approach that we took to kind of tackling this problem, the results that came out of that, and then finally just some conclusion, future directions. So if there are any questions, of course, feel free to ask throughout the presentation. Otherwise, you can ask at the end. So what is AOSP? Briefly, Bender. It's basically the core of Android, right? It's the everything from all the frameworks to all the extras to everything that makes Android run, and then of course the modified Linux kernel. We focused, for the purposes of this research, on the API that was in android.jar, which is obviously the jar, the Java archive that represents the Android API that your application can work with. Our research didn't include private APIs, so things that weren't open sourced by Google, or third-party APIs, so things like HTC, any of the HTC things, the Samsung, any OEM provider or any vendor API that wasn't included in AOSP. So just briefly, permissions, otherwise known as capabilities. In Android parlance, they're called permissions. These are granted at application install time by the package manager based on what's declared in the Android manifest, that nice little fat XML file that talks all about what the app is going to do and what its name is. So these include things like internet, send SMS, read contacts, vibrate, which my phone just did, etc. And typically these permissions are checked. The bearer of these permissions, being the app that's calling some function that requires this permission, that permission is checked at the time of a call. What we're going to see throughout this presentation is that these checks are sometimes done in an inconsistent way, and we'll give you a few examples of those. So these calls might be include creating a socket object, which of course is just a wrapper to underlying socket functionality in Linux. Higher level things like accessing Bluetooth, which of course is an abstraction of accessing Bluetooth hardware. Starting an app's activity, calling like the main browser window. Maybe there's a permission that's checked to actually let an app call that, and so forth and so on. And content providers, so things like SMS and contacts list and things like that, you need permissions to actually access those. Some of the problems with the problem domain that we're encountering here, the Android API reference documentation is generally pretty good about saying for a given class and a given method in that class, or all the methods in that class, you need this permission to do anything with them. But it's not 100% complete, and in some cases it's inconsistent. It will say you need permission X. Well, permission X doesn't exist, which we've actually seen. Really, you need permission Y or Z. So that's interesting edge cases like that. There's no explicit map that says to a developer, hey, you want to send an SMS. Here's the method you need. Well, I mean, SMS is probably a bad example because that one's well documented. Follow me. You want to send an SMS. Here's the method that you need to call, and here's how to package, the data to send it. Here's the permission you need to request in your manifest. That's at a functional or implementation level, this map doesn't exist. this is obviously not going to happen, but developers who really want a deep understanding of this will need to really read source code to see what permissions are being checked, which is something we're trying to solve. The consequences of this, of course, and I apologize for the font. I chose this really awful color scheme many moons ago for a different presentation and just decided to keep it. We have two cases, undergranting of privileges and overgranting of privileges. So undergranting is really typically, not 100% of the time, but typically a stability and usability issue. If you think of when you get that nice little force close thing that comes up, and if you're looking in the Android log, you'll see like a security exception was raised or thrown. And it gives a little bit of detail. It's because the developer called something but didn't request the permission that was required to call it. And it leads to a force close because they didn't write an exception handler. Overgranting is really can typically be more of a security issue, something that AppSec folk might want to be a little more concerned with. If you think of mobile AV apps, which request every single permission known to man that's available in Android because they need to do so many privileged operations on the phone, if a lot of them use native code, like Lookout, for instance, not to pick on them, but they're the one that comes to mind. If there's some sort of exploitable bug there, rather than having to take over the phone and get root, you just send bad data or interact with that privileged app in some way. Your malicious app effectively inherits the capabilities or permissions that has. The overgranting issue comes into play where they ask for all these permissions, the developer asks for all these permissions for their app, but never calls into code that actually exercises any of those permissions. So why does this happen? In some cases, developers just don't have time to sit there and come up with their own maps for everything and figure out what permissions they need for something. They just know, well, my app crashed when I called this, so I'll just throw a bunch of permissions into the manifest until it goes away. And then maybe that code never really gets called that exercised the permissions they added, so effectively they're over-granting. So I'm breezing through some of this. Why isn't there a map? Well, AOSP, obviously there are many versions of Android. It is somewhat of a moving target. It evolves over time. New permissions get added, new permissions get removed. So the nature of AOSP, or Android Open Source Project in and of itself, makes it kind of hard to just sit there and focus on one particular version and build this map out comprehensively. Google has actually said, sort of passing in the hall at Black Hat, that this is of interest to them, but it's not priority. They feel, and I'm paraphrasing, that what they have is good enough for developers to understand, and by and large it is. So they get a point there. The difficulty of generating the map, as we'll see in some of the examples upcoming, makes people kind of glance at this problem and go, it's fine, I'll just continue to run my source code scanners and my cool Python scripts that find permission-related issues. And then finally, there's no wow factor to this. For the most part, there's nothing like cool exploitable bugs in generating this map. You're not going to find anything that's really interesting. It's more of just a kind of a mostly academic research study, but it has real-world implications, which I'll explain later. If you know what Veracode does, you'll see why this is interesting. Some other things, the API is pretty massive. You have to figure that every single class and every single method therein is potentially a candidate for something that's going to check a permission, so we have to add in logic to see if a permission is required to enter into some code. I'll get to that. The complexity of source code, changes in source code, new commits to Android tree might introduce problems around this. And then, as we'll talk about in a moment, some dynamic analysis difficulties. One of the previous research projects from UCB that I'll mention tried to approach this from a dynamic angle and with mixed results. So some data points. This is the class count over the different revisions of the API from 4 up to 16, where 16 represents Jelly Bean. There are, start probably about 2,200 classes in version 4, up to approaching 3,000 unique classes in API 16. And then for each of those, a grand total of probably 20,500 or so total methods in 16. So you can see it's generally like a nice, upward number. So each of these again is a candidate. The number of permissions, a lot of people who don't do Android stuff on a regular basis may not be aware that there are actually 130 unique permissions in API 16. Not all of them are ones that are things you can request in the manifest. Some of them are like, a little more private permissions that are only granted to system applications and whatnot. It should be noted that this number is not aggregate, like this is not just a constantly increasing number, because between, say, here and here they might have added 2 permissions but taken away 2 permissions or renamed them. In some cases they did things like, instead of calling it access, they called it read. So they revoke certain permissions and add certain permissions. Interestingly enough, Nick Kralovic from Google politely called me out and corrected me, and I'm glad he did, on another presentation I did. But in API 16, the read logs permission, so in Jelly Bean, that doesn't exist anymore. They found it to be too much of a hassle. Too many people were screwing it up and using it the wrong way, and leaking information that they, or retrieving leaked information, that they just revoked it entirely. So even very prominent permissions like read logs are just no longer there, and that's happened over time. So with regard to the complexity of source code, so there are typically a number of ways that permissions are checked, standard ways that are very easily identifiable, such as check calling or self-permission, where you check if a given permission exists or has been granted to the calling application when it calls a method in some API, and if Android.permission.modify audio settings has been granted, then we return true, and this check audio settings permission works great. However, even sometimes there are less identifiable ways, and such as, like, here we go, if basically bind accessibility service dot equals service info dot permission, basically just doing a comparison, and if that's valid, then this function completes, or doesn't complete based on whatever. But this is not actually calling a method to check that permission. It's just saying, does this object equal this object? If so, then we assume that the permission is granted, therefore do something, which makes it a little harder to identify where permission checks are actually happening. Routing through iBinder, which is a kernel mode driver that the Android team created, that does a lot of security enhanced RPC and IPC stuff. Some of these calls can actually be wrappers or routers into iBinder interfaces, which may be implemented in native code, and therefore the check might be occurring in native code, and that can be tough to identify all these levels of abstraction to where the check is actually happening. And I'll show an example, not iBinder related, but something that represents this problem a little bit later. In API 16, there are roughly 9,700 files and a total of about 2 million lines of executable source code. So just to further reemphasize how complex this surface really is. So that's really the static side of things. From a dynamic side, which has its own merit, there's a lot of stuff that we have to execute. We have to identify candidate methods and classes and how they work, and to call them, and do we grant permissions or do we not grant permissions, and then how do we instrument the app to see when an exception is thrown and what the permission was that was required. So there's a lot of code to generate. We have to sit there and wait for everything to run. We have to wait for everything to crash. We have to restart it. Method arguments, is this polymorphic? If we pass it one object type, is it going to act in different ways? Is it not going to check a permission? We have to identify all these different code paths and how to properly call each of these methods. System state. Some things require one operation to occur before another operation can occur, before the permission will be checked. This is a problem that the UCB researchers encountered. And then, do we run things on an emulator versus hardware? Because there may be things like NFC or some of the low-level radio stuff that can't be emulated properly, and therefore it's not really accessible. So we can't really call into that and get the same kind of response that we would get from a physical piece of hardware. And then finally, retrieving test results. How do we actually find where the error occurred and make sense of that? So some prior research. UC Berkeley researchers wanted to do a static permission map. I think they called it static permission requirement verification. This was last year. They took Android 2.2 and as interesting, I think it may have been done for Fortify or something, or sponsored by them. they wanted to build this nice web-based map you could work with. They realized the challenges of doing static approach to this, so they ended up taking a dynamic approach. They modified the Dalvik VM and some other core components of Android to return more verbose information about what the error actually was when the security exception was thrown, and give more detailed information about what permission was required when a method was called in a class. They used randup, which is a JUnit test case generator, to generate the bulk of their actual Android apps, and then built them like you normally would, and then just had devices or emulators to sit there and run those, emulators to sit there and run those, and then watch that log output. The problem that they ran into was factory classes and constructors and methods that maybe had required certain operations to occur and maintain system state. They just bailed on those, so they only got, I think, with the first pass, like less than 80% coverage, but in the second pass, that when they modified this, they actually got 80% coverage. So their second approach was to develop their own test case generator and package these apps up and run them. And they covered more than what was just in Android.jar, so they actually did call into some private frameworks and some Google private frameworks. But it actually, the downside to this was they actually had to modify the Android source code, which isn't, infeasible, but it's a little more work than, I want to do in like my basement or something. Required human intervention, so there actually needed to be, a log monkey to sit there and go, okay, well it crashed, we'll extract that out and plop it into this exceptions list, so we can go back and refine the test case generator so it'll account for that. And it wasn't fully automated, which we're all about automation. The results are public, but the tool set that they used and the means of replicating their research was not made public. So they just talked about like what they did from a very high level and the other tools they relied on, and then gave you the results. And furthermore, they only covered revision 8 of the API, so Android 2.2. Obviously, that's not representative of all of Android now. A second major piece of research, L-E-L-E, French university, I think. It's not French? Well, it's the University of Luxembourg, so I assume that that's probably somehow related with. Anyway, another team they wrote a tool called COPES, or Correct Permission Set, in May of this year, so right after we had started working on our stuff. They used Soot, which was another Java analysis tool and call graph generator, to do this. So the nice thing there was it built more accurate call graphs, but they had to also there was also human intervention, because they had to go and say, okay, this is the entry point for this is the root of the call tree, and there's actually someone building that out, which isn't terrible if you have a large enough team, but still requires some human intervention. When there were things into like service manager requests, telephony service, Bluetooth, I don't think Bluetooth has a service manager, but some of the more like complex service manager calls, which get a little muddled, they actually had to like kind of enumerate all the classes and methods that were related to those service manager calls, because those are things that require like state. There's a little bit of heavy lifting there. The nice thing about that was the no need to modify Android source. Using something using Soot, they could feed a lot of the existing like output from there back into Soot, like specifying entry points and stuff, and kind of have like templates to basically work with, I think. They had better results than UCB, we think. So that their approach was static, but a little bit better. The downside to this, of course, is that there was still a lot of human, like heavy lifting from humans to specify entry points, do all the service call stuff, and back to the permission checks inconsistency problem that I talked about before. When they encountered permission check types or methods of checking permission that they weren't used to, like the enforced calling or self permission, etc. When they had like dot equals, they just kind of bailed on those. So they had to go back and I think refine some of those, or they just discarded them entirely. So finally, because this is what you really care about, our approach, we originally wanted to take just a purely static approach. So okay, we've got the Android source trees, we've got android.jar, we've got cscope. Let's go to town. Let's see what we can do with just these things, and never run an app, right? Our results with that were mixed, pretty good, but not good enough. So, taking a cue from the UCB researchers, we decided to build a hybrid, take a hybrid approach and build a dynamic tool to use some of the static results as sort of a seed, and then augment the static results with dynamic validation of some of those, as well as finding some cases where static might not have found a permission check correctly. And this was all written in Python and with a lot of really vulgar comments in some of the some parts of it. So static analysis. Like I said, we wanted to use cscope. If you're not familiar with cscope, in a nutshell, it's a powerful source code indexing tool. Supports primarily C, C++, and Java-ish. We found a few issues in cscope's lexer in the way that it was identifying the names of some of some methods and certain small subset of classes, but enough that Andrew went back and actually modified this cscope lexer to properly this is actually a method, don't stop here. But ultimately, the simple diff and patch made it pretty easy. So the first step was to identify and generate a list of the normal permission check methods. So check permission, check calling permission, enforce calling permission, check calling or self permission, so forth and so on. Anything that was identified in the API and through the docs as being this will check a permission. Then use cscope to sort of not really, I don't know if you're going to call it a call graph, but just say, who's calling me? Who's the parent that's calling me? So here's a permission check, trace back up and find where basically the entry is, right? Map that back to API calls and stuff that was in android.jar. And then finally glue all that together and say, okay, this is the method that's being called in this class, this is the permission that's being checked, and this is the means of how they're checking the permission. Is it one of these methods that up at the top? Is it just a comparison? And furthermore, the permission that's being checked, is that the only permission being checked? Or is it is there another requirement, or is it this one will satisfy or this one will satisfy? In some cases, we actually found, especially things around native code and whatnot, which we'll also talk a little bit about in a second, there were actually of value were comments that said, hey, if you want to call this, you're going to need this permission, because that might actually be a callback into native code or iBinder, or a call into another class somewhere where the permission is actually being checked. That's a little fuzzier, but it did actually have some value. And then finally, like every good Python script or sort of hackish approach, we stored everything in a SQLite database, and then wrote a bunch of really crappy scripts to dump all that stuff out. So from a dynamic analysis side, once we had all the results from the static analysis side, and I'll show some of the output from that. The stuff that was identified in the static map was then fed back into another wrapper script that actually would basically write out, really horribly, write out a bunch of Java, just Java source into what would later become an Android app. So okay, well, this particular, get neighboring cell info, go ahead and write out all the calls to that, build it properly so it receives the correct arguments, and then eventually, once that's all built out, compile the app, package it up, sign it, run it in an emulator, and then another wrapper script sits there and watches the output from logcat and says when an exception was thrown and if there was more detail there. So runs the APK, builds the APK, runs it against an emulator or hardware. Mostly it was run against an emulator, and then finally, like I said, parses logcat output. So we really ideally did these in batches, so we didn't have like one APK that called like this portion of the API and this portion of the API and this portion of the API. We said, okay, service managers first. We're going to call all those. So that'll be the service manager APK or set of APKs. Static method calls just the bulk of the Java API or Android API. Then specifically pulling out classes that don't have or aren't a constructor, and then ones that are constructor classes or have in them constructor methods. And just by kind of like grouping these things together, it was easier to identify when problems arose, or if we needed to go back and refine this. This sort of, as Andrew likes to say, stabilized testing. It's a very academic way of putting it. So some examples of service managers, just to give you some idea. So like Wi-Fi manager, audio manager, telephony manager. These are things where we actually have to basically like say, me.context or this context get system service, whatever the handle is to Wi-Fi service, since that's a system-wide thing, not just unique to our app. So that's an example. We had to build little snippets like that, and then if we didn't have the permission to open, we didn't have like any of the appropriate Wi-Fi related permissions, an exception is thrown, and we get like a nice error validating our static analysis, our original static analysis map. An example of a non-constructor case, like I said, some of them don't have constructors. Like a Bluetooth device, for instance, we get the default adapter. That's kind of like I think the Wi-Fi manager would be an example of this, but maybe not. If it's like a system-wide thing, since there's we don't have an object that is our unique Bluetooth adapter, it's sort of like so it's not really a constructor returning the object, it's returning like a handle, basically, like a system-wide handle to this. We had to identify those and then write little snippets that would just, if we don't already have one, go ahead and open up a handle, so to speak, to that, and then interact with it in some way. And then an exception would get thrown, and we would hopefully validate our static results. Then back to just simple things. So anything that was generic was like a simple constructor, or most of the regular Java API and Android API stuff. We would just identify simple primitives like int, long, float, etc. Common things that you're used to if you've done Java stuff, throwable list, string, socket, stuff that's we called common. And then finally identifying just Android-specific things like context, parcel, which is basically the root of a lot of message passing stuff, iBinder, intent, package manager, etc. And then what, for some of those, so for some things we're going to call in dynamically, we need to just have like basically a big nice list or array of what arguments we'll be feeding into the methods that we pull out of static. So our automation wrappers, if you've ever built an Android app by hand, Ant to compile and build, AAPT to package all the resources, jar signer to put a crappy fake cert in there, and then finally zip-align to optimize it. Zip-align's not necessary for this research, but since we're already killing our emulators and some of our devices, having as much optimization as possible in there for running these apps is really nice. And then finally, yet one more pair of wrappers that actually start up the emulator or talk to push or install and run the app on the device. Sit there and monitor tail logcat, and grepping out for certain expressions that look like a logcat, a security exception being thrown, and then pulling that information out and dumping it into back into the database in the same format. And it also handles automatically, building, installing, uninstalling the previous one, launching it, etc. So parsing logcat, we learned, is it's super hackish, but it's kind of, I don't really know of a better way. So typically we'll see, java.lang.security exception. Okay, easily identifiable. When you see that and you see, like a warning and system.error or something, cool, we know that an exception was thrown, and we can parse the rest of that and find out what the permission was required. In this case, device power, when calling the go to sleep method in Power Manager. Pretty easy. However, it's not always 100% effective, because since one developer was like, I'm just going to raise a security exception. The other developer on Android might be like, I'm just going to spit out some stuff just called permission denial. So I'm just going to write out literally like a log.w permission denial. Here's some information, rather than raising a security exception. So in this case, set speakerphone on method was called, and it just says permission denial. Okay, that doesn't really tell me like what the error actually was, what permission was actually required to call that. It makes it a little kind of a pain in the neck to parse logcat output. Or finally, java.net.socket exception. Since that actually is e-access that's raised from Linux, then Java, the Dalvik VM itself throws java.net.socket exception, permission denied, rather than a security exception in some cases. So our results were pretty good. We didn't require modification to any Android source code. It takes about 15 minutes to do the static analysis, or an average of 15 minutes across every version of Android, of AOSP, sorry. And then about 1 hour to do the same for each revision of the API dynamically. And I believe that was only on one emulator, so okay, that's pretty good. There's not a lot of human intervention required. The dynamic stuff actually took more effort to go back and validate some of those results and shove them into the database, much like UCB did. But the static side didn't really require any human intervention once we felt it was ready enough. Compares about accurate with UCB, especially for 2.2, since they only did 2.2. We don't really have any other maps to compare against, and like I said, we can run it against every version of the SDK. So like I said, we can only compare against UCB's map for revision 8, but if they decide to do another one, maybe we can compare against that. The nice thing that they had that we didn't was stuff that wasn't just explicitly in Android.jar, so private methods and things. But what we covered and what they covered compare pretty well. So since they were sort of the first ones to really do this, that we kind of figure that they're a decent bar. The bad, it doesn't cover all methods. So back to the native code thing. Some methods are just JNI stubs, and when they enter into native code, that's where the permission check's being done, and we don't cover those right now. That's where the dynamic side comes in. We can get a little more information about that. Here's an example. The permission check is actually, so this is C++ code. The check permission function is actually being called to see if access surface flinger permission has been granted, and if so, then this. I forget what function this was, but it'll proceed somewhere in Surface Flinger, the Surface Flinger source code. And it's also not in the AID graphics user, whatever UID that is. If this hasn't been granted, permission denied. But then of course I like this. Back to the example of very inconsistent logging. Permission denial, can't access Surface Flinger UID PID. No information about what permission was actually required, because maybe the developer is not actually going to go read the source code. So that kind of presents a problem for us. Abstract classes, we're kind of working on that right now. I think Andrew is putting in some stuff for abstract classes. Subclassing all those abstract classes in the dynamic side, but from a static side, that's a little more of a pain in the neck. Again, only limited to AOSP, no Google private frameworks or third-party frameworks. It does require changes to cscope, not so hard. It's literally like a patch. AOSP source trees are required. This I think this took a day plus to check out every AOSP source tree, because I'm lazy and I don't want to sit there and use the repo tool to branch and go back and whatnot. So it's just easier to, for simplicity's sake, to check them all out all at once. So this, I think, each of these was roughly counting all of the the whole .git directory and .repo directory. I think each one was average of 5, maybe 10 gigs in the higher end. So that's significant, but it just takes a long time. But disk space is cheap. So if you've got a fat pipe and disk space, this not an insurmountable problem. So some practical results that came out of our analysis. Here was a sanity check that we did, just to make sure that our call graph analysis from the static side was sufficient. We basically just took a class that was well documented and had the permission check that was the permission that was required to call to do anything in that class. That we like, let's just make sure that our results don't suck. So in Bluetooth Health class, it explicitly says requires Bluetooth permission. Requires Bluetooth permission for get devices matching connection states and unregistered app configuration, just as a couple of examples. So it's pretty well documented. I apologize for the terrible text, Sublime text dump here, but here's just an example of dumping some stuff from the DB. So here we just have the revision that we were focusing on, which was 15. So Android.Bluetooth.BluetoothHealth.connect to channel source method. In this case, here's the class, here are all the methods, here's the permission that's required, Android.permission.Bluetooth, and then finally the way that it's being checked. So enforce calling or self-permission is the checking method. That's the permission that's required, and for each method. So in this case, documentation is superb, permission requirement is accurate, and they all check consistently, and that's great. Examples of where this called out a few issues that were not known. In the Wi-Fi manager class, for the start scan method, the documentation doesn't say what you need or what permission you actually need. This is from developer.android.com, and I still don't think it's been updated. So if you know anyone at Google, tell them to fix this. Here's just a simple block from the source code. Start scan method. Blah 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 blah. Enforce access permission method, which gets called. Enforce calling or self permission. Checks to see if the access Wi-Fi state or change Wi-Fi state permissions have been granted to the caller. Contrast to the documentation, and then finally the output from our tool, which, oh by the way, for pretty much everything in the Wi-Fi manager class, you need access Wi-Fi state or change Wi-Fi state, and luckily all being checked consistently. So that was cool. But that's an example, and there are other edge cases like this that you are free to explore. Another example, telephony manager, and actually I think I have some. There was a chunk of notes that I probably need to. Oh, God, what a piece of crap. Yeah, hold on. Anyway, just for clarification, I'll mention this in a second. But the documentation, even I checked it today, still says that the access course updates permission is required to call get neighboring cell info. This is actually a known issue on Google Code, the Android bug tracker, 19192 for those interested. So the access course updates permission doesn't exist. It's not a real permission. I don't believe it's ever been a real permission, but it could have been lost somewhere in the deltas of permissions added and removed. So even in the source code, it says, oh yeah, you totally need the access course updates permission. Basically, telephony managers get neighboring cell info actually calls the phone interface something, I forget. Effectively, it just calls another method in another class, but we traced it back, and our tool actually worked. To get neighboring cell info, enforce calling or self-permission, access find location, or access course location. So either of these permissions are sufficient for this, for get neighboring cell info, but the documentation says you need a permission that doesn't exist. These are one of the two permissions that's checked. Finally, our tool output says access find location or access course location, and this is the way it's being checked. So, it's kind of funny that this is totally inaccurate, but it's an example of just an oversight on Google's part, and these are plenty of these to be had. So the conclusion, the too long didn't read with a cat. So this would be great. I think this would be really helpful, or we believe it would be really helpful for developers and for application security people who want to learn if an app has been over permissioned or under permissioned, or just to get an idea of when you're writing your nice report, bro, what issues might exist. Again, there are strange edge cases where permissions are enforced inconsistently or checked inconsistently, or the documentation doesn't match what the developer actually thinks. And really, it would be cool if Google had control of this, since they have all the resources and appropriate access to everything Android related to really work on this. But we're giving it our best shot. One of the other things that we learned was this was a good exercise in understanding what not to do. So, as probably a lot of talks generally go into, this was a nice way of saying, oh, okay, so we should really have a more consistent naming scheme for permissions and for the means of checking those permissions. Having maybe a more consistent API for developers, or even platform developers, app developers or platform developers, to check whether or not a permission has been granted. And then a map that keeps track of all the API calls that require permissions and what those permissions are. So ultimately, our future plans really include refining the static discovery. So I don't think that we'll get the abstract class stuff solved necessarily, but it would be cooler to have, like, I don't know, stuff that isn't just in Java. So maybe all of the native code stuff that actually does permission checks, having that handled from a static side, and that'll really help with enhancing the dynamic analysis as well. In the dynamic side, appropriately subclassing all abstract classes and not just the ones that were sort of haphazardly chosen. Yeah, so I think there will be some stuff around this talk posted up on the Veracode blog. So it's veracode.com/blog, company shameless plug, and look for that hopefully within the next month or so, or upcoming weeks. Yeah, and if you wish to contact any of us, that is my email address. That is Andrew's email address. Those are our Twitter IDs, and there's Veracode, and then a bunch of greets to people. So, yes.
So one thing that I'm curious about is you talked about trying to find some way to check permissions in the native code. Is there some single point of native code functionality that all of the permission checking goes down to, and if so, couldn't you just hook that?
So it kind of goes back to the same problem with the Java side of things. So like you saw in the surface flinger code, there's actually a function that's called that checks the permission of that calling task, right? But there's also stuff that's like equals equals, like actual just comparison operators that we get muddled into that again. Really, I'm going to be honest, just getting through identifying all of the Java based checks, permission checks and comparisons, and all the different really horrible inconsistent ways it was being done, at that point it was just like, okay, that's pretty good, let's work with that for now. So that's on the horizon, and that's something that we want to do next. But yeah, there are some ways it's still going to require, like I think the C-scope, some of the C-scope indexes that we built focused primarily on Java. Like if we take one index, there's no mention of C or C++ source files in there anywhere. So we can't like resolve a symbol in a Java file and then like have C-scope index that across C.
It seems like the easy way to do this would be a debugger that just actually like watches the block of memory.
Yeah.
For the permissions info and traps every time you enter that.
So one of the other things that I've kind of planted in this research project's collective mind, there's a tool by Scott Dunlop from IOA, or used to be at IOA, called Anbug, and it's really an Android app debugger. Well, I mean anything that supports JDWP, it'll let you attach to as long as it's marked debuggable. That's something that I've kind of thought we might be able to leverage. So like just trace when anytime a check is anything that looks like a permission check is being called, and then log additional information that way. That's just haven't done it yet, but that might be another way. Yes.
So one of the quickest and dirtiest ways to check for overgrants was one of the things that you mentioned earlier that someone else had done, where you just build an app whose manifest requests no permission, and then see what it can actually do. Have you replicated that at all? And if so, have you been tracking it for multiple Android APIs?
that was the first approach we took. We were like, oh, let's use Randup. We actually wanted, the first step was to replicate the UCB research, because we were like, okay, they set the bar pretty high. Let's reach for that. And we used Randup to build a bunch of Android apps with JUnit test cases with no permissions, calling every single method in the API. We haven't really gone back and done that across the different versions because we ended up taking the static approach, focused all our efforts on that, had pretty good results, and then we're like, okay, well, let's take the best of both worlds. Let's like use the what we did with Randup, but instead of just saying, okay, for everything that's in the API, call it. We were like, well, let's give it first the validation of what we found statically, then go back and fill in the gaps.
I'm curious as to whether the number of overgrants for zero-perm apps is in fact monotonically decreasing like you know it was.
Right. Yeah, I don't know. Right now, the data is mostly really raw and sitting on
In a SQLite
sitting in a bunch of SQLite databases on a server I can't reach right now. So yeah, I think hopefully that'll be. I'm not promising anything, and I know I'm on camera, so hopefully that would be one of the things that we would hope to release on like the blog is here's some stats on what we found.
So also you mentioned at the beginning, this isn't sort of confined like zero days or anything like that. But one thing that occurs to me this type of research could lead to is searching for places where you can call functionality without the necessary permission.
Right.
You should have that permission. Did you find anything like that, or was that anything that you were looking for, a place where you would expect the permission to be required?
I will go back and look through because I'm willing to bet a coffee or a beer that there are cases where that
considering the number of different
right.
ways they do the check.
But the thing is, so it's our tool doesn't prove the negative, right? Like it doesn't say, oh, well, here's a method that you can call that says it requires a permission. It doesn't. We're saying for every method that requires a permission, here's the permission that's required. So I go back and just basically do the inverse, right? So that would be not listed, but that would probably be another. That's really more of like the academic side of things. The first step was like proving that an app is over permissioned or under permissioned. The inverse would then be to build the opposite map where you can reach into things without a permission.
Just thinking of this from
right.
The attacker-defender perspective, the attacker wants to release an app that doesn't tell you it sends SMS,
right.
but actually does. The defender, Google in this case, probably wants to make sure that they patch their software so that you can't.
Yeah, I was talking with someone earlier about interesting ways to go and have an app basically modify its own. Well, I mean, this is a path to explore, but like how could you modify your own entitlements, basically? How could you?
Like the Java breakdown with Apple's.
Right. Like what's the possibility there for an Android app, and how does this relate? But that would be that's another interesting approach. So. Cool. Well, thank you for coming, and be around for a bit. So I think there's like a thing after the thing. Probably involves beer. So I'll be there. Cool. Thank you.